All right, so in this video, we're going to be looking at operations on matrices. And so the simplest operation on a matrix is to add two matrices together. To add matrices, they must be of the same size, and then we add corresponding components. So if I want to add the matrix 1, 2, 3, 4 to 7, 8, -3, -2, then I'm going to add the 1 and the 7 to get 8. And then I'm going to add the 2 and the 8 to get 10, and the 3 and the -3 to get 0, and the 4 and the -2 to get 2. And then that is my resulting matrix from the addition process. Now, if you're going to do subtraction, they basically work exactly the same way. You would just be subtracting corresponding components instead of adding them. Now, scalar multiplication is another operation that we can perform on a matrix, and scalar multiplication can be applied to any matrix of any size because we're only dealing with a constant and one matrix. And this is also going to work by adjusting every coefficient, every constant inside the matrix by the same thing. So in this case, I'm taking my 1, 2, 3, 4 matrix and I'm multiplying it by 2. And so I multiply 2 by 1 and I get 2, and 2 by 2, I get 4, and 2 by 3, I get 6, and 2 by 4, I get 8. So every entry gets multiplied by the same scalar. Now, matrix multiplication is much more complicated, but we're going to walk through an example. Now, matrices that are being multiplied do not have to be the same size. Unlike when you're adding them, they have to be exactly the same size. But for matrix multiplication, they don't have to be the same size exactly, but they do have to have inside dimensions that are the same size. So if I have one matrix, which is m by n, and I have a second matrix, which is n by p, then I can multiply them in this order, where the n of this first matrix matches the n of this second matrix. So the number of columns in the first matrix matches the number of rows in the second matrix. And then the resulting matrix will be of dimension equal to the two outside dimensions. So the result will be m by p in this case. So let's look at a specific example. Here I have a 3 by 2 matrix, and here I have a 2 by 4 matrix. So in this case, 3 is my m, and 2 is my n. And then in this matrix, 2 is my n, and 4 is my p. So this is a 3 by 2 and a 2 by 4. The two inside dimensions match, and the resulting one will be a 3 by 4. Now, the way that this is going to work, and the reason that the two inside dimensions have to match, is we are going to multiply the first row of the first matrix by the first column of the second matrix, component by component. So, if you've used dot products before, this is like doing a dot product on this vector and this vector, this row and this column. So this 2 will get multiplied by this 3, and this 0 will get multiplied by this 1. And so the resulting entry in our matrix will look like this, which will end up being -6. And then we will continue from there in the same manner. So the next entry will be this first row by this next column. So 2 by 5 and 0 times 6, which will get me 10. And then 2 and 0 times -7 and 4. So 2 times -7 and 0 times 4, that gets me -14. And then 2, 0 times 8, -5, 2 times 8 and 0 times -5 gives me 16. That's my whole first row. And then I continue with the next row in my first matrix. So second row, and then by each one of these columns. So -1, 1, by -3, 1, -1 times -3, 1 times 1 gives me 4. And then -1, 1 by 5, 6, -1 by 5, plus 1 by 6 gives me 1, -1 by -7, and 1 by 4 gives me 11, -1 by 8, and 1 by -5 is going to give me -13. And then I repeat the same process for the third row. This is 3 and -4 multiplied by -3, 1. So 3 by -3 and -4 by 1. That gets me -13. And then 3 by 5 and -4 by 6. That's going to give me -9, because this is 15 and -24. And then 3 by -7 and -4 by 4 is going to get me -37. And 3 by 8 and -4 by -5 is going to get me 44. It is very difficult to undo matrix multiplication, and we will have strategies for doing that. But matrix multiplication is quite complicated, and it does take some practice to get used to lining up these rows with these columns and not getting them confused. And again, notice the result here. We multiplied a 3 by 2 matrix by a 2 by 4 matrix. The 2's matched and then disappeared, and the resulting matrix was a 3 by 4. Now, again, partially because of this level of complication, when you do matrix multiplication, you are not guaranteed to get the same result when you switch the order of multiplication. So for example, if I were to treat my first matrix in my first example as A and my second one as B, I get a result that is a 3 by 4. But if I flip the order of multiplication and try to multiply B by A, then they're not actually, that multiplication process isn't actually defined, because the 3 and the 4 would not match. They would be the new inside dimensions, and they don't match. So that's not defined. But even when they do match and they are equal to each other, these two matrices are not going to necessarily be equal to each other. And this non-commutativity is one of the sort of the hallmarks and the tricky parts about working with matrices. Even if they're, say, square and you can freely multiply them in either order, the result is not going to be equal on both sides. Now, there are certain special cases where they will have the same value, regardless of the order that you multiply them in. But in general, they will not necessarily be equal. And so we can't assume that AB and BA are equal, even if they're defined. Now, associative and distributive properties do still hold, but you do have to, again, be careful about flipping the order, because that won't work. Now, another operation that we can perform on matrices is called the transpose, and it's indicated by this raised T kind of in the exponent position. And essentially what it does is it turns rows into columns and columns into rows. If you have an entry for A that's Aij, it will become Aji of the transpose. So here's an example. I have this 3 by 2 matrix, and this is the transpose matrix. This 2, -1, 3 in the first column is now 2, -1, 3 in the first row, and 0, 1, -4 in the second column is now 0, 1, -4 in the second row. And it's the same thing if you read across the rows and then turn them into columns, you'll get the same thing. So this first row is 2, 0, and here the first column is 2, 0. Here the second row is -1, 1, and the second column is now -1, 1, and the third row is 3, -4, and now the third column is 3, -4. So it doesn't matter if you think of these as columns or rows, you're just converting one of them into the other one in the other matrix. And then either way you think about it, it'll be consistent when you're done. Now, an inverse matrix is a matrix so that if you multiply it by the original matrix or another matrix, you get the identity. And unlike matrices in general, inverses are commutative with the regular matrix. So A inverse times A is equal to 1, equal to the identity, and A times A inverse on the other side is also equal to the identity. Now, the simplest way to find the inverse matrix, particularly as your matrices get very large, is to use this augmented style process for finding it. And the idea here is that you start out with the matrix you want the inverse for, and you put next to it in your matrix the identity matrix. And you perform row operations, which we'll talk about in a little bit, on this matrix in order to convert your the original A matrix side of this larger matrix into the identity, and then the second side of the matrix then becomes your inverse. And we'll walk through this kind of process more when we talk about row operations. But basically, the idea is you're doing elimination on your matrix. And once you find your inverse matrix, then you can do matrix multiplication. And when you multiply these two matrices together, you get the identity. And again, you can do this in either order. Now, for a 2x2 matrix, there is a formula for calculating the inverse matrix without having to go through this process of using the identity matrix. And the formula basically looks like this. The determinant in the denominator here for a 2x2 is AD minus BC. But the entries in the matrix basically involve flipping the locations of A and D and then changing the sign of B and C. Now, if you have a larger than a 2x2 matrix, there is no general formula for something like this that is in any way easy or computable. It is really only for 2x2 matrices where we can get a nice simple formula. As the matrices get larger, there are expressions that you can write, but the entries are not just entries in the larger matrix moved around. There's actually more computation that's involved in getting those entries, and so we're not going to go there. In a formal linear algebra class, you might get to see the formula in one of the sections, but I, in particular, don't tend to teach it because it is computationally kind of a waste of time. There are better ways to get inverses than those crazy formulas. Now, we mentioned in the inverse matrix that there is a thing called a determinant. And so we're going to actually talk about determinants in general a little bit. Determinants are a number that is calculated from the entries in the square matrix and only square matrices that can be useful for determining whether an inverse exists or not. Essentially, determinants, because they're in the denominator of our formula, they're going to act like division by zero. So if our determinant is zero, there's no inverse. But if the determinant is not zero, then there will be an inverse. There will be a way where we can find a matrix, we can multiply by our original matrix in order to obtain the identity. But you can't multiply zero by anything to get one in multiplication. And so there are some matrices that where these inverses don't exist. Now, for a 2x2 matrix, the determinant is basically just A11 times A22. So that would be these two diagonal entries minus the product of the two off diagonal entries. So for this determinant, this 1, 2, 3, 4 matrix, we get a determinant of -2. Now, so that means there is an inverse for this matrix. Now, the notation for determinants, sometimes you'll see them expressed like this, where you have DET as the determinant notation, and then inside the parentheses, you put your matrix, either the matrix itself or the name of the matrix. But you may also see just absolute value bars in place of your regular matrix notation. Those absolute value bars are not treating entries like they're absolute values. This is the determinant notation. We're not going to use that notation in this discussion, though. Now, for a 3x3 matrix, we have a process where we can break our matrix out into smaller matrices using submatrices and then calculate the determinant from there. If you've ever done cross multiplication with vectors, it's basically the same process. So here we're going to expand out along our first row of our matrix, A11, A12, A13. When you expand out like this, you flip the sign alternately. So you start with a positive and then a negative and then a positive. And if you have more terms, you would keep flipping. And then the determinant portion that gets multiplied by this coefficient is going to be the original matrix with this, in this case, this coefficient entry where you cancel out both the row and the column that that entry is in. So if I cancel out the first row and the first column, the determinant that gets multiplied by A11 is this bottom corner, A22, A23, A32, A33. In the second term, the A12 coefficient, besides being negative, gets multiplied by the determinant that cancels out the first row and the second column. So A21, A23, A31, A33. And then when we do the A13, we cancel out this third row, or this first row, but the third column, and it's this determinant that gets multiplied, A21, A22, A31, A32. And then we would use our rules for the 2x2 determinants to get those determinants of these submatrices. And then we could finally multiply by the entries A11, A12, and A13 and combine those to get our final answer. So let's go through a specific example. So here we've got first row 1, 4, -2. And we're going to multiply 1 by the submatrix from this corner, 9, 3, -5, -1. Then we flip the sign, -4, and then the determinant of this 1, 2, 3, and -3, -1, because we're leaving out this middle column. And then plus our -2 times the determinant canceling out this part of the matrix. And so we're left with 2, 9, -3, -5. And then from here, we calculate our determinant. So the determinant for this 2x2 is 9 times -1 minus 3 times -5. And then in this one, this is 2 times -1 and minus -3 times 3. And then here, we're multiplying this determinant, 2 by -5 minus -3 by 9. And what we end up with over here is -24. And this one becomes -28. And this becomes -34. And we end up with a determinant of -86. It's not 0, so there is an inverse. But we'll find that when we actually do calculate the actual inverses, we're going to end up with 86 or some reduced version of lots of fractions with 86 in the denominator. Now, some properties of determinants are that if you switch a row or a column with another in the matrix, that will change the sign of the determinant. So if we were to calculate the determinant on a matrix that was just like this, but maybe we switched row 1 and row 2, the answer would come out to be positive 86 instead of negative 86. If the matrix determinant is 0, then the matrix has no inverse. In linear algebra, we refer to that as being invertible. If it has an inverse, it's invertible. If it's not invertible, then there is no inverse. A strategy for finding the determinant of very large matrices is to use row operations, which we'll describe below, and then convert the matrix to an equivalent triangular one, because then the determinant is just the entries on the diagonal. This may be easier than working out the formula using submatrices, particularly if the matrix is very large. In the case of the 3x3 determinants, the signs are plus, minus, plus. In the 4x4 case, they would be plus, minus, and so on. You would, each time you go down the row or the column, you change the sign. Now, we use the row 1 as the basis for our formula of expanding our determinants, but you can use any row or column of the matrix to do this, and you should get the same answer unless you've made an arithmetic mistake. If you have entries in your matrix which are 0, that will greatly reduce the number of operations you have to do, since everything is 0 if you multiply by 0. And so you may find that it's easier to choose a particular row or column to do your expanding on in order to simplify and take advantage of those zeros. Multiplying a row by a scalar multiplies the entire determinant by that scalar. So if you multiply the entire matrix by a scalar, then you're actually multiplying the determinant by that scalar to the power n, where n is the dimensions of the matrix. And remember, determinants have to be done on square matrices, so n is both the number of rows and the number of columns. So if you multiply, let's say, a matrix, a 4x4 matrix by 2, then you're actually affecting that determinant by a factor of 16 because it's 2 to the 4th. Now, if you're working in your TI calculator, there is a determinant function in the calculator that you can also use to check your answers. Although, of course, in class, you may be required to show your work. Now, row operations are things that we can do on matrices, particularly for working with augmented matrices to find solutions to systems of equations, or in the case of finding the inverse of a square matrix, we also have a process that involves doing row operations. Now, row operations, there's basically 3 things that you're allowed to do, and 2 of these come from the process of elimination by addition, basically. They're just the matrix equivalent of that solving systems of equations process. But there is one additional rule, because in a matrix, we care about the order of entries, whereas in a system of equations, we really don't. And so one of the operations that you can do on rows is to switch 2 rows. You're allowed to do that freely. It doesn't change the solution. It changes the determinant, but it doesn't change the solution. You can multiply a row by a scalar. And so that would be like multiplying an entire equation by a scalar. And you can also add 2 rows together with or without multiplying by a scalar. Again, this is a process of elimination that we were working with when we were dealing with systems of equations. We would multiply by a scalar and then add the equations together in order to try to eliminate one of the coefficients, one of the variables. Basically, the same thing is going on when we do row operations. While we can use these just sort of in general or for other processes, you do tend to use this for solving systems. And so you want to turn locations in your matrix into zeros when you can, ones that you're not using, so that you can eliminate them essentially from the equation. So let's go through and use this augmented matrix to find our identity using row operations. Now, for row operations, the first thing that we would like to do is get this top entry A11 to turn it into a 1. So the first step is either to swap rows of your matrix or to divide your row 1 by some constant in order to turn whatever is there into a 1. And then we're going to use that 1 in order to try to eliminate the entry below it, turn this 3 in this example into a 0. So I'm going to multiply sort of off to the side row 1 by -3 to get this. So 1 times -3 is -3, 2 times -3 is -6, 1 times -3 is -3, and 0 times -3 is 0. And then I'm going to add this to row 2 in order to get this -3 and +3 to cancel and turn into a 0. And then the rest of the row, -6 and 4 is -2, -3 and 0 is -3, and 0 and 1 is 1. And so now that's going to become the entry in my new matrix. I'm going to replace row 2 with that. So what does this operation look like in notation? I took -3 times row 1, I added it to row 2, and then I replaced the old row 2 with this expression, with this row. Now I want to continue then to, once I have everything below this A11 entry turned to 0, then I move over to the next entry, and I want to try to turn this entry down here into a 1. Now, there is sort of a mechanical process that you want to go through if you're doing this, but when we're working sort of by ourselves, we can be clever and kind of save ourselves a little bit of steps by not having to do something and then undo it in order to do something else. So the next step after turning this A22 entry into 1 is to turn this entry above it back into 0. And so I'm going to actually do this turn to 0 first, since these are already opposite signs of each other. And then I'm going to turn this -2 position into a 1. So if I add those together, R1 plus R2 put back into R1, this doesn't change as a 1 because the second row I already turned to 0. And when I add those two entries together, this 2 and this -2 canceled. And then I have to remember to add these other two positions together as well. So adding these two, I get -2, and adding these two, I get 1. And that's my result. And then finally, to make this side my identity, I'm going to essentially multiply. Actually, this notation is a little wrong. I'm going to divide this row by -2, which is to say I'm actually multiplying by -1/2, not multiplying by -2. That's a typo. And when I divide by -2, then this position becomes 3/2, and this position becomes -1/2. And this thing right here, this is now my inverse. And in fact, we saw earlier that when we multiplied this inverse by the original matrix, we did get the identity. Now, when we want to do things like switching rows, it's generally for a situation like this. Again, this is not something that the calculator will always do, but it is something that we can do to make our life easier. In the calculator, what they will tend to do is they will just sort of plow ahead as long as this first entry is not a 0. And what that would do is if you divide this top row by 3, you will introduce fractions. And the calculator may not particularly care about using fractions, but it is going to take longer if we are trying to use fractions ourselves. And so we may prefer not to do that. So one thing that we could do with this example would be to take row 3 and move it up to row 1, and then we would already have a 1 here, and then we could continue solving the rest of the equation without introducing fractions on the first step. Now, the calculator will switch rows if the A11 entry is 0, and then it will switch rows in order to make it non-zero in order to proceed with the rest of the calculation, because you can't have a 0 entry in this top position if you are going to try to solve the system. So it has to be some non-zero entry to start with. But for our sake, we will tend to, if we have a 1, we would like to put the 1 there so that we don't have to do any divisions. All right, so in the next video, we're going to talk about working with systems of equations and converting systems of equations into our various matrix forms.